Today we wanna calculate Latin square design, and this is a kind of a topic used to analyze data in statistics. And this one, you're given a data like the observation arranged in rows and column. This is the observation, and we have different observations, and the observation here are D, S, S, O, C, and C. So right away, when we wanted to analyze this data, we just add the row total and the column total first, like this. Row total you add directly like that. This is how we do it. You add this plus this plus this plus this plus this, and you get the total. This is the row total, and you do it continuously up to the last step here. Next we go to add the column total. Column total is this one, and this one. You had to find the total. So remember, this total here, this one will give you the same answer here when you had this one, and this one. So that is the first step you are going to do when you're analyzing this kind of a Latin square design data. The second thing, you're going to find the degrees of freedom. Degrees of freedom, here we have degrees of freedom of rows, columns, the treatments, and error. And degrees of freedom here, this row we have degree of freedom of 4, and this is by subtracting 1 from the total rows we have. We have rows, we have one row, we have row number 1, row number 2, row number 3, row number 4, row number 5. You subtract 1, you get 4. You do the same to the column part. Here we have 4, and it is 5 minus 1. Or you see how many columns do we have? We have 1, 2, 3, 4, 5, and that is the number of total minus 1, the number of columns we have. Then we have treatment, the same thing. The treatment have this observation, and they are arranged in row and column, so you find there is 5, just the same, 5 minus 1. And then the error here you calculated by the formula V minus 1 times V minus 2, and this one, V is the number of treatment we have. We have 5 treatment, that is 1, 2, 3, 4, 5. So we have 5 treatment, that is 5 minus 1, which is 4, and then 5 minus 2, which is 3. 3 times 4, you get 12. Good. So next step, you move to find the treatment. Here is where you're going to classify this data into similar observations. We have observation O, we have observation S, 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 D, C. So you find the total of this O treatment. So this is how we go about it. Go in the first row, we have O, that is 6.6. The second row we have 36.4. Second row we have 67.5. Second row we have the other row we have 53.2. Then the last row O, we have 70.9. So this one, when you add, you find the total. This is the total of O. Similar to S, you come again, find S. This is the S value. You add the S value like that, and this one is 73. Find S, this is 54 plus 55.6 plus 68.9 plus 76.0. You get the total. You get the total of S. You do all through the same thing to up to the last step where C. And remember, this total of treatment this total of treatment should be equal to this total of observation under rows and column. So we move the next step to find the sum squares total. Then total sums of squares. Total sum of squares, you are going to square all this observation we have. We square this plus squaring this plus squaring this, squaring this, squaring this, squaring this one. You square all of this, you square all of this, you square all of this observation. Then you, after squaring all this observation and adding them, you are going to subtract the correction factor. The correction factor here is the total here. This is the total we have here squared. That is the total squared over the total number of observation. This we have 25 observation. That is, we would say 1, 2, 3, 4, 5, and then times 1, 2, 3, 4, 5. That's 25. So you get the answer. That is the correction factor. So you subtract that, you get the SST. That is the total sum of squares. You find the answer to be that. Next, you come and find the row sum of squares. Row sum of squares. Here we are going to square these rows values here, the total rows. You square this, you add square this, you add this, square this, add, then square this, then square this, and you find the answer as that. But this time round we are going to divide by the number of rows we have, that is 5, and then the value you are going to get, you subtract from our correction factor, which previously we had found to be 108,860.4036, and you find that then you move ahead and find the column sum of squares. This one you're going to add you square the columns, square the columns, you square this one, you add and you square this one, plus square this one, plus square this one, plus square this one, plus square this one. You find the value and you divide by 5. Divide by 5 by the number of columns we have. We subtract from our correction factor, which we had previously gotten, and you find the answer. The next step, you find the treatment sum of squares. Treatment sum of squares here is the total of all the square of all the total observation under treatment, which is for this O we square 264.6 plus 328.6, 338.6 plus you square all this, you square 364.6, you square plus 328.4 plus squared plus 338 squared plus 372.9 squared plus 345 squared. You divide by the number of treatment we have, you get 5. We subtract our correction factor. So after analyzing that, you come and find our ANOVA table. In ANOVA table, we always have the source of variation, the degree of freedom, the sum of squares, mean of sum squares, and then the F ratio. Okay, we find the rows, we had the rows, and we gotten that the degree of freedom of the rows, sorry for that correction, degree of freedom of the rows was 4, degree of freedom of column was 4, treatment 4, and 12 for error. So the sum of squares is the value we gotten earlier, but remember here we did not have the error, the sum of square of error. This is gotten by adding. This is adding the total. We always know that the total sum of square is equals to column sum of square plus row sum of square plus treatment sum of square plus error sum of square. And we already have the total sum of squares. And having the column sum of squares, the row sum of squares plus the treatment sum of squares and plus error, which you don't have. So this one is a very simple mathematic. You had this, and this, then you subtract from this and you get the error, and there you go, is the error. Find the total. So because we are only interested in treatment only, you find the sum of squares, the mean sum of squares of treatment, which is given by the formula m. The mean sum of squares here is the mean sum of squares is the sum of squares of treatment over the degree of freedom. That is the degree of freedom. We have. So we have with this one as the sum of squares of treatment, and then we divide by 4 and we get this value, and we only put our interest under error. Therefore it is 2 or 2.05 divided by 12 to get the value. So after dividing the value, you are going to find the F ratio. The F ratio here you got by 321, that is 321.13 divided by 16.84. So you find you get 19.1. Sorry, get 19.1. Now when you're comparing this thing here, we always have the null hypothesis. Null hypothesis is always the treatment 1 is equals to the treatment 2. That is the null hypothesis. And the alternative hypothesis, we always say that the treatment 1 is not the same with the treatment 2. So this one, suppose we are comparing it to 5 degrees of freedom, 5 significant difference. This value from the table is always 3 point, depending with the F ratio table. That is, you get the value of v minus 1. That is, and then you get the value for error, v minus 1, then v minus 2. So this one you get it was 4, and this one is 12. So from the table you get this value to be 3.26. So you find that this value 19.1, the value you got in the F ratio, this value, the F ratio is greater than 3.26. This means we are going to reject the null hypothesis and say that the conclusion here will be what? There is no significant difference. There is significant difference. Sorry, there is significant difference. There is significant difference because the treatment observation of OSSC are different. It means there is a significant difference in this observation. So that is how we go about calculating the Latin square design and analyzing the data. Thank you.